Well, this lecture introduces multinomial regression model designed for analyzing nominal response variables. When a variable is nominal, the categories cannot be ordered. There are two things that are unique about the nominal variables in terms of its quantification. Okay, first of all, the difference or the distance among different value categories of this, of nominal response variables don't have numerical meaning. Okay, and second, the ordering and the ranking of the value categories of nominal response variables don't have numerical meaning. That is, ordering and ranking don't matter anymore, unlike the ordinal response variables. Models for nominal outcomes can be used when the outcome is ordinal. This is done since it avoids the parallel regression assumption, sometimes called parallel lines assumption or proportional odds assumption. And there may be doubt as to whether the variable is ordinal. Plus, a researcher might be more familiar with the multinomial Logit model. If a dependent variable is ordinal and a model for nominal variable is used, then is a loss of efficiency since the information is being ignored. And here, I want to talk about a table that discusses what's going to happen when there's a perfect match between the true level of measurement and assumed level of measurement, and when there is a mismatch of the two. So here, for these columns, we have nominal to ordinal to interval to ratio variables. And as the arrow goes, the more quantitative the type of variables becomes. Okay? And here we have assumed level, also from qualitative to more quantitative. What's going to happen when the assumed level is more qualitative than the true level? And we use a modeling technique designed for the assumed level. So here, for example, okay, so if the true level is, let's say, ordinal, more quantitative, than nominal, okay? And we use a regression modeling technique, in this case, for a nominal variable, which is multinomial regression model, for a ordinal response variable, the true level, okay? Well, what we will get is inefficiency, okay, inefficiency. That is, it's going to affect standard errors. But in terms of, let's say, accuracy of regression coefficients or parameter estimates, they're still ballpark close to the true population numbers. Okay? Well, let's flip it. What's going to happen? What's going to happen if the assumed level is more quantitative than the true level, and we used modeling technique designed for the more quantitative level measurement for the less quantitative true level measurement? Here, again, I'm going to give you an example, right? Let's say, okay, the true level of measurement, is ordinal, okay, is ordinal. But let's say we use regression technique designed for more quantitative response variables. In this case, would be interval or ratio type of response variables. Let's say OLS regression. What's going to happen? So we use OLS regression, okay? Technique designed for continuous interval ratio response variables for a true level measurement of an ordinal response variable. Okay, what's going to happen? Well, biased estimates. Okay. Right. So what really is multinomial regression model? The multinomial regression model is like simultaneously estimating binary logits for all possible comparisons among outcome categories. It is a simple extension of the binary logit models, but the challenge with this type of model is that there's a large number of comparisons, basically pairwise comparison, right? If we have, let's say, 3 categories, later on we will have an example for that. Then we will have 3 pairwise comparisons. And if we take into account the order of comparison, let's say which compare with which, okay, we can flip it. Then it's going to double, right? It's going to double. So lots of comparisons and hard to talk about the results. And here's an example, a nominal response variable y with categories L, S, and P, and their corresponding subsample sizes NL and subscript S and subscript P, right? And here L corresponds to laborers, menial labor. S is skilled workers. P is professional, so occupational status. And some literature indicates that this is a nominal level variable, right? There's no numerical meaning in terms of the difference across these 3 categories, regardless whether that's division, multiplication, addition, or subtraction, or the difference, or ordering. Okay, so here is a graph of these 3 categories, right? And we can make pairwise comparisons. Well, if we want to check into the effect of education on the odds of laborer versus skilled workers, then what we're going to do, we can run a binary regression. We can select corresponding subsamples. Here is n subscript L plus n subscript S observations with outcomes for y equal to L or S. Then we can estimate this binary logit, right? Log of the odds. Recall my discussion of binary regression models. And we can have intercept and a slope for education. And for the slope, we have 2 subscripts, right? One is correspond to education, right? 1, the first slope. And then the second subscript denotes the odds comparison. This is laborer versus what? Skilled workers. In terms of interpretation, we're going to say, well, for a unit increase in education, odds of L versus S going to change by a factor of E raised to the power of that slope number, right? And the remaining comparisons can be analyzed in the same way. For example, if we're interested in, let's say, odds of S versus P, we can do similar estimation, right? And if we're interested in the odds comparison of L versus P, and we can run a third binary logit regression, right? So to some extent, multinomial logit model can be viewed as a combination of separate binary logit models. But under the framework of multinomial logit model, it is done simultaneously. Here is another feature of multinomial logit models. That is, we can always derive log of odds and its corresponding regression coefficients from other odds comparisons. So here's an example, right? So this is the first log of odds, and this is second log of odds. Okay. Relying on the fact that log turns division into subtraction, multiplication into addition. And if we carry through the computation, we will get the sum of these two log of the odds is equal to the last log of the odds. Okay? And we can check into the details of the calculation. And you can stop here and carry through the computation here and see what's going to happen if the result holds. Okay, and this leads to one feature of multinomial Logit model, that is, there's a minimal set of coefficients. So in last slide, I showed you that the last pair of probabilities, or the last log of odds, can be derived from a simple linear combination. Here is the sum of the first two log of odds. Okay, so log of the probability L over the probability of S plus log of the odds of P, the probability of S over the probability of P is equal to the log of the odds L over P, right? Then we also have right-hand side terms, right? On the right-hand side, we have intercepts and slopes, right? And they also have that relationship, right? So for the first log of odds, we have this equation. For the second log of odds, we have that equation. And for the third, we have this equation. And the sum of the first two intercepts, is going to lead to the third. And the sum of the first two slopes going to lead to the third. Well, when I say sum, it really depends on the relationship of odds here. Later on, I will show you, okay? We have to be very careful. Sometimes it's sum, sometimes it is what? Subtraction. So in this case, in this particular case, we can have this relationship, okay? More generally, you can find a coefficient for any comparison from a pair of other coefficients. Here, we have this regression coefficients, right, from the multinomial Logit models, okay? And here, I'm talking about a generic variable. So a single variable here, but across different log of odds equations. Okay, I'm not talking about the relationship between different covariates. I'm talking about the same covariates, okay? Either education or income or something, okay? So for the same generic covariate, its slope, okay, for the odds of L over P is equivalent of the sum of the slope for the odds of L over S plus slope of for the odds comparison of S over P for the same covariate across different equations. So to memorize it, because it is related to the property of log, okay? So if we write like that, then S can cancel out. So here, right, if we take these two out, is L over S, S over P cancel out. It'll become L over P. So this is a convenient way to figure out the relationship here. So if this is L over S, how we get that? Well, for this two is L over P. And subtraction for log, it turns into what? Division. So it becomes P over S. Again, when we cancel out, it becomes L over P. Same thing for the last equation. These relationships hold when I talk about same covariates, okay, from multinomial Logit models.